Anybody? One definition of what's a reliable system? It just works, right? So if you go and switch on the light, you want that light to just work. If you go pick up a phone, you just want that to work. So it just works is reliability essentially, right? So if you say that you have mechanical systems, how do you measure reliability? Mean time to failure. You keep stressing the system in real world conditions and then say that after how many iterations does it break. If you take software system, then what do? You again stress the system. What are the problem with what is the fatigue in the case of software system? It's your memory leaks, your state rot, and long range dependencies and stuff like that. That kind of leads to when a software is running for a long time, it'll break. Whereas when you're testing it for 5 minutes, 10 minutes, it'll all work. So that's reliability. So when you say that there is a service that's like running, and then if you say that there is a downtime, and like that's a problem. And if you say something like hey, I'm like 0.995 is my reliability, that's fantastic. If you say 0.95 is my reliability, that's not so much, because in that case you are talking about billions of transactions. In that case, that 0.5% is like a significant chunk of people who are getting impacted. So if you fundamentally think about reliability, it's like the bar that we have so far seen are all super high. Now when you come to AI, do we get anywhere near 0.9, let alone 0.95? Absolutely not. You have to celebrate those instances where it did a fantastic job saying, look, it worked, right? Those examples is what you're really looking for. So now, but what do people really look for? When you go and give a product to people, again, think about it. There's a big difference between selling your product to who's the power users versus sharing it with the end users. The bar for simplicity need to be super high. Like one of the things that we I used to talk about is that you can look at all the people in 5 categories. You have your super early adopters, then you have your power users, then you have your mainstream users, then you have your late adopters, and you have your I don't want to change my systems people at the end, right? So if you go look at in real world system, the people are going to be a full distribution across these 5 categories. But across all those people, what they are looking for is reliability, right? But the level of reliability that they are expecting is very different. For early adopters, the reliability that they are looking for is when I show a demo, will it work? They are not looking for will it work? If I use it million times, when I use it 1,000 times, does it work? That's not the question. But if you go into mainstream users, it's like whatever are the tasks that I'm dependent on to get things done, will it solve 90% of the time? So exception handling can be for 10% of the time, but 90% of the time will it work? So that's the point. Fundamentally, if you look at user, this is what they are looking for. For AI system, it's like, can I count on the output? If the LLM comes and tells you that, hey, the usage of this particular feature is 92%, the engagement level is so and so, you should be able to trust that number. If you say something like, what is the root cause of X? Why is this failure trending up? If you go ask that question, and if the LLM comes and says something like, oh, it's because of this particular change got deployed or whatever, you should be able to trust it. But when you dig in subsequently and then say that that's not the real reason, trust breaks, right? So fundamentally reliability. So now let's look at some of the things that we have seen. Like these are all 3 snaps. The first one is from Copilot, second is from ChatGPT, third is from Gemini. What do you see? Can make mistakes. Really? AI is doing something for me, but like there is a disclaimer that says that it can make mistake. Can I trust this output or not? Right? Why is this happening? I mean, I'm not saying this UI is wrong. I don't want us to go and lie about it. The point is today the tech is not at a state where you can go and tell that everybody can confidently say that it's AI generated. You still want that. Hey, this is AI generated, but they don't have to go put a disclaimer that says that this can be this can be wrong. How do we kind of reach there? So what are we looking for? So the first one is verifiable claims. If you say something like, hey, this is trending down because of this change got deployed, or this is a system change that's happening, or this is an outage that's happening. If there is a root cause that's coming like this, you want to be able to go and tell that, okay, why are you saying I should be able to click through to go and say something like, okay, that's the root cause, I trust this data. So that's about verifiable claims. Second thing is, you not always you will have humans involved in the pipe. there will be systems. So in that case, systems, again, think about it. So you have your AI systems and then you have your traditional software system. That's like if you think about our body, your brain, and you have your muscles and all. So the muscles, how it is going to work, that does not require like really that much thinking and stuff like that. It should just like, work. So in that case, all you're really doing is send a signal, it'll pull, right? That's the motor actuation that you're talking about. In software systems, it's like this. When you say something like call this function, it should just work. And traditional software systems work like that. So if you think about any systems moving forward, you will see these two layers with AI systems. There will be a layer at the bottom, which is just like traditional software, which will do the work. And then there will be thinking layer that's on top. So when you do like this, the calls that's originating from AI layer should be able to properly orchestrate the calls in the below layer. If that's not happening, you have a bad system. And that's where structured outputs are super important. AI can handle, between A string and B string, AI can handle very, very well. But if you go and call a function saying something like instead of uppercase A, if you pass lowercase a, and if the condition check is not handled correctly, it'll break. It's brittle, right? And the third one is strict instruction following. Like there are many prompts that I have seen, which will say something like, oh, you must do this and blah, 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 all that. It doesn't happen. And you go and like tell something like, what if I remove this line? Does it make any difference to the output? It doesn't. But then why are we putting all that in the prompt? Because we feel like if I instruct all these things, maybe the LLM will do it correctly. All the statement that I said there is a source of lack of reliability. And lastly, I don't know is a good phrase. There are times if you ask me a question and if I don't know, if I say I don't know, it's a better thing than if I say something and then you're like, it's more confusing than before. That's worse, right? So AI today cannot say I don't know. I mean, stylistically, it can say I don't know. If you go and write instruction that says that if you're not sure about it, then go and tell I don't know and stuff like that. Sometimes it will fire up and then say I don't know. But can you rely on that prompt? No. That means it's a great proof of technology. The technology is in the right direction, but the technology has not matured to a point where you can clearly separate from I don't know versus, oh, it knows what it is talking about, right? So with that, let's kind of look at, again, briefly touched upon the previous slide, which is how do these two things relate? If you look at software system, why is software system very reliable? In software system, we constrain, like in a second year, I remember we studied discrete structures. So one of the things there is you distill all the things down to those discrete types. You say that these are all the objects that are allowed. These are the semantics of how the software will work. And within that, that software will work. So if you go and take a software, which is, let's take Excel. It's generic enough, but still Excel is specific. How is Excel specific? Excel says I can handle all the data in a grid. Each cell can have string or numbers. Numbers can be interpreted into these known types. That's it. All operations, like there's over 1700 commands that are possible in Excel. All those things are well defined around those types. And so the software system is very reliable because of this. You can practically go and tell that this is the state that's allowed and these are the operations that are allowed. Everything around that, everything else is disallowed. Whereas AI is not like that. These are like universal machines. So what's essentially happening? Chat is an unconstrained universal interface. So when I come and talk to you, I can ask any topic in the world. But you will come and tell something like, oh, I'm not equipped to go talk about that topic. You will tell, like humans will tell. AIs don't tell. They'll just like, try to go fill something about it and then continue. That's a problem. So the interface is like this. If you take a UI has restrictions. Excel has grid. It says that you can input number only in this grid form. Whereas in chat interfaces, you don't. You can enter whatever you want. The second problem that you have is that the single big model problem. So you say that the whole system, large language model, you have like trillions of parameters. All those things are in this one giant model. You can't practically meaningfully contain what that certain part of the system is capable of doing and what is it allowed to go and perform. That's the second big problem. So is single big model helping? It created a breakthrough, but should we continue like that? To be explored, to be learned. The last one is a very interesting one, which is 2023, many of the people would have talked about hallucination, hallucination, hallucination. And if you go and say, okay, what is hallucination? Like, again, think about it. Hallucination for human being is like, you are you are high, and then you're kind of hallucinating. It's a mental state. But here, hallucination is just imagination. And if you see what is imagination, there is a distribution that says that all these values are possible, and you're sampling from there. Whether that sampled value is actually there in real world or not, the system does not know. The AI does not know. And that's the reason why you end up with some kind of output. And many times, right, like what does creativity means? If you tell something like, I have this possibility, what else are not yet done? That's creativity. You're trying to go identify the things that are possible that are not yet done, and you're trying to say that I want to go explore those things. That's creativity. So from one perspective, that property is useful for us with AI. But if the creativity is getting applied when you're doing a fact check, that's not useful. Make sense? So with that, if you see, I'm going to skip this one. The main point that I want to say is this fusion of having a single big model is a source of all these challenges that we are talking about. So with that, let's kind of take a step back and then say, this reliability is nothing new, right? What can we learn? You have aeroplanes, you have cars. So let's pick cars. So how did cars progress? Is it decent enough? Yeah, it's decent enough. So the very first car, I think it's from Benz, the leftmost one, right? And that's not how you see today, right? So that car is practically you are strapping a motor onto a system of wheels. That's it. And from there it kind of evolves to a point where in 1950s, if you see, you get into this car. But what's the problem in this car? It's still not very reliable. It'll break down. When there is an accident, it's going to be like really bad. It's too heavy. By the way, I don't know how many of you have experienced Ambassador car. If you see like 90s Ambassador car, and if you try to close the door, my God, that was heavy. Right? Whereas if you go look at today's car, you just gonna go and move it. Like my kid can go do it very easily. And that's the difference. So what changed? What changed is systematic experiments. You kind of take the system, break it apart, identify how each part contributes to the outcome, and then say that how can we simplify, how can we enhance, and that's what happened. So all the crash tests, all the aerodynamic experiments, everything finally contributed to a car like this. Now if you go and say something like, okay, should we keep waiting to take a technology that is like this and then wait till the technology bakes to like this? No. Why? Because we were able to go and ask people to go work on developing a car like this only because of the economic value that got generated along the way. Without that, there's no industry to go and develop. You have to make people buy all those early products. Much in the same way, even with AI, if you say something like there is a very primitive tech right now, we should just go and wait for everything to be perfected. It's responsible, it's reliable, it's aligned to our values, everything. If you go put everything and if you say that only till then we will wait to go ship this particular product, it's not going to come there. So what we need to do is we have to progress along the way, look for people to say that at this point, who are the people who can tolerate the reliability that we are having right now. But at every point of that stage, what we need to be very clear about is what reliability level are we in? And today that's missing. So let's kind of see how to go and think about it. It's like, we need to kind of systematize this to say something like what are the phases of development that goes into such things. And if you see that initial phase, it's basically like I think it's too small to read. I'll just use the bottom one to kind of highlight the point. If you look at phase 0, phase 1, phase 2, it's really to go and tell that how do you mature the tech to make it economically useful? You are really going and telling that is this tech, if developed, can we go make economic value out of it? Which means can we make a product, can we sell it to people, can we extract something out of it? That's what you are really assessing during the first 3 phases. If during that, if either the tech is not maturing well or if it is not deployable broadly, then you don't go in. 2 examples I'll cite. Take rocket ships. 1969, man went to moon. After that, are we having our annual vacation in moon? No. At least people during the 60s, they thought that, oh, eventually we can go to moon for annual vacation, but that's not going to happen, right? Why? The economic system is too costly to go and support something like that. It's not possible. Let's take another thing, fusion energy, right? The tech itself is not there, right? Like, the aspiration could be there, but the tech is not there. If the tech is not there, it's going to take a lot of time. So that's why if you go look at all these things, it's a good idea to kind of see whatever tech that we are seeing, where are we right now? And if you see the phase 3 to 4, if you see phase 3 is where the industry gets developed at scale. You are like really looking at, if you look at car industry, the assembly line gets developed. You are really looking at, how do you distribute, how do you manufacture, everything gets figured out at that point. So that's really phase 3. Phase 4 is where you are like telling that the reliability problems and science problem kicks in, where you are really saying that if I sell this particular product to people and if they return the product, how am I supposed to go deal with it? That's going to be lost. So that's where you'll start like thinking about the reliability problems. And lastly, if you look at the phase 5 is really the science, right? Today, if you go look at AI, I would equate AI, the knowledge in AI that we have currently as an overall industry as alchemy versus chemistry, right? Alchemy is you're wishful for saying that can I go mix these things and get something useful out of it, and then you try so many things and something works. When something works, you kind of keep repeating the same thing over and over again. Take gunpowder as an example. Gunpowder you mix, somebody figured it out accidentally and they continue to go use it. Versus now you go and tell something like without chemistry, you can't really go model what will be the yield of it, etc., etc. You can't go model. But once you have the science behind it, like think about atom bomb. Before even the bomb was made, people were able to go and calculate what is the expected yield. Yeah, there were some errors here and there and stuff like that, but at least you had a model to say that where is it going to land. That's not what happened with gunpowder. Gunpowder is like I lit it, it burnt, yeah, it works, right? It's a functional comparison. That's what happens in phase 1, phase 2. But if you have to really mature an industry, you need to be at phase 5. Without that, we are not matured. So now comes the question: in AI, where are we in this continuum? So let's look at it. So I'm not going to go all the way to 1950s, right? So let's start somewhere, right? So that's more like a wishful thinking state where people saw the possibility and then they said, hey, let's extrapolate. Right now, let's start from GPT-3 moment. Why am I picking this moment? Why not, ImageNet moment? ImageNet moment, in my opinion, is still phase 0, like early form of phase 0. This I'm calling as phase 0 primarily because of the generative AI that can be applied usefully, right? So if you look at GPT-3, it's practically statistical world knowledge. So what happened at that time? You basically do next word prediction training across the complete internet content. Complete, it's massive, right? What the base model is capable of doing is it can understand the information. It can't generate in a meaningful way. Then you go slap supervised fine tuning on top of it. And when you are doing a supervised fine tuning, what it can do is you give like a few short example. And this is what I tried in like 2021, which is you have to generate an output and then say, okay, I'm going to ask you this question. Then you say, here is example number 1. Here is example number 2. Okay, example number 3 is the actual question that the user is posing. So this kind of few short examples that you can give in 2021 and you get some output. But it's not guaranteed to be correct. Your context window was also fairly narrow. If I remember correctly, it's around 2000 tokens or something like that only. It was fairly narrow, right? But the thing that was very clear at that time was extremely strong proof of tech. Nothing before that can match what was possible at that time. That is very clear. Now let's go into ChatGPT moment. What changed? More supervised fine tuning, and more importantly RLHF, which is reinforcement learning with human feedback. So this mechanism basically says what do people prefer, what kind of output do people prefer, not necessarily just text completion, but text completion is tuned towards output that we can understand meaningfully. So by the way, for those people who haven't like tried some of the early models, if you go give, there will be times where the model will start generating the same token over and over and over again. And by the way, that happened even in 2024. Even last year it happened with GPT-4 model. So you just like give, and depending on the context, it will start like hallucinating. So those problems still existed till last year. So, but the beauty was because of RLHF, the output is now more reasonable and reachable to more number of people. And that led to within a month, ChatGPT was able to go to 100 million users within a month. That's fantastic. Never heard of before. Now think about it. That 100 million could have died down. That went to 900 million primarily because of what all happened subsequently. So let's look at the next moment, which is a tool use. So if you look at previously what was happening, um, by the way, if you look at what happened along with ChatGPT, any tool that you need to go and develop during this period means you have to invent your own DSL, domain specific language, or you have to go and say, okay, generate some code, and you have to write lots and lots of parser to say that, can I make sure that whatever tool that it is indicating is actually there? All the check you need to do. It was not reliable. It breaks. Again, the problem is this, right? If you say 1 out of 3 trials will work, that's really bad. That's how it was at that time. With tool use, the key breakthrough was that you can do what's called as constraint decoding. In constraint decoding, what you do is like, how many of you are like don't know about how the sampling works at the end? When you say that every token is getting generated, the way in which a token is generated is model will only say this is a probability distribution of all the possible tokens that can come next, all. And then what you do is you pick one among them, and you can do a random pick there, or you can say that I will do a probabilistic sampling. So what the constraint decoding did was, in addition to just doing a sampling, let me also see whether it is following the syntax correctly. The syntax of, is it a JSON structure or not? Is it the expected JSON structure or not? That check made a big difference, and that's the first time where we could see the first sign of improving reliability. So no longer you needed code scaffolding that said something like check whether the string has all these things, like look for triple tick, look for 3 backticks. None of the check was like needed after that once this breakthrough came. So again, once this came, agent development became easier. Then we go one level further, which is the orchestrators that happened somewhere around 24, late last year, early this year. This is when couple of 3 changes happened. The first one was a more reliable orchestration patterns to say that if you are talking about code gen, these are the type of tools that are needed, and this is how the agent loop is supposed to be. If you're generating document generation, this is the pattern that is needed. If you're looking for enterprise information, this is the pattern that is like needed. That orchestration patterns became more and more clearer. The second one that happened is the reasoning loops, which is test time compute, where you go evaluate multiple things and then you assess what is going to work and then evolve based on that. And the last one that was very good is the long context. You remember 2021, we are talking about 2K. Now you can go all the way up to 1 million, 2 million. Even the frontline models right now support 128K of context length. Pretty huge, right? So all these changes essentially brought the continuum that we talked about towards phase 3. And this year, if you see agentic coding, I said this in the morning also. It's like practically you can, if you put all the scaffolding around what spec you want, how are you going to test it, what are the build instructions it should follow, if you specify everything and if you unleash the model, it can run for one whole day. By the way, that's what I was able to manage so far. But the plan is to go to several days continuously. But with that, what you can do is code generation can practically be unleashed. It's just like delegated to systems to say generate the code. And if you are very systematic and methodical in defining the scaffolding, which is scaffolding in this case is how do you build the code that you're generating? How do you test that the code that you've generated fits into the rest of the system? What are the tests that you should be running? And then put all these things into an agent harness loop. And that's why personally I would view this as killer app of AI. Everything else is awesome. Everything else is great. But the economic value that this can unleash is just phenomenal. Number one. Number two, the tech that's enabling this is also great, because if you think about the previous one, you need to collect lots and lots of human samples, and that's a scaling problem. But whereas when it comes to coding, you can practically go and tell that, hey, I'm actually creating a RL loop. In this case, what's the RL loop? Whatever code that you're generating, make sure that it's building. Make sure that all the tests are passing. Just that becomes like an automated feedback signal. So it's fantastic. So with this, what am I saying? We are at phase 3. This means there is a very clear-cut value of saying, using this technology, we can create this kind of product. Very clearly established. Such a product is useful for people. That's also clearly established. Now it's a point to go and say, what would it take for us to go to phase 4 and phase 5? And if you look at what is phase 4 and phase 5, it's really to go and tell that how do you drive reliability and how do you kind of get to the science of how the system can be controlled and made predictable. Okay, so now with that, any question before we go further? Questions about the state, anything that's not clear? Proceed. Cool. So if you look at the requirements, I want to just highlight the 5 things. Number 1 is the output validity, which is whatever output that is coming, is it following the structure that I'm asking? So if you say that, hey, prepare a deck for me, PowerPoint presentation for me, it should prepare PowerPoint presentation, or the structure should be matching that. If you say that go drive the system, it should be able to go drive the system, no extra signals, no missing signals, etc. The second one is separate known from inferred. See, this is a very, very important one. This is to say that if you ask a question to the system and if it is answering that question, you should be able to clearly separate from what is actually known. Hey, this information is this because of this. Very clearly, you go cite it to a specific source, or sometimes it's inferred. Inferred means you are saying if A is true, B is also true. So you're telling I'm going to infer this. So in that case, that inference should be claimed that way. If this is true, I know this is true because of which this is true. It need to be like that. And then the third one is admitting uncertainty and unknown. And this is what we talked about earlier, which is if you don't have enough information to go make a claim, just say that it's not certain. Like, example is, let's say you have an agent that's like, okay, let me give you this. So let's say you are part of a team which has developed a product and the middle of the night, your service has a problem. What do you think is going to happen? Let's say sign in is failing. Such an important requirement, right? Sign in is failing. What happens? The engineer who is involved in that work gets a call, right? Incident alert. If that person is still sleeping, then his manager gets a call. And then their manager gets a call and it goes all the way to the CEO. Right? Of course, in between somebody will catch it. But the point is that I had one day, there was a call that I wasn't part of that incident loop. Suddenly I got a call at like 2:30 or something like that. I just woke up and I was like seeing 4 to 5. Okay, wait, this number means something. And then I took a call. And then from 3 o'clock till like whatever 7:30 or so, it's just to go and take care of that, to go and address it. Now, what you want is an AI agent that takes care of this. And in that case, the next day morning, when I say that whether it is taken care of correctly, I want to be confident that it did a good job. If it is like, oh, it is mess, I would rather say something like, wake me up. I don't mind. Just wake me up because it's not worth it. So that's what we are talking about as that reliability. So in that case, admitting uncertainty becomes a super important requirement, which is in that case, you're saying, I don't have enough information. I need to wake up somebody. You need to be very clear about that. And then the last one is reliable instruction following. Consider the same case of following this instruction for how do you go deal with incidents. Let's say that engineer has spent a lot of time failure modeling and then say that these are the paths to take. If the AI is not following the instruction correctly, despite you have given all the instruction, you're not going to trust it. And then the last one is learn from usage, which is if like today, all models are like this. They are 100% like, what is that movie? Gajini movie. It's like at the end of the session, reset back, it's not going to know anything. It is absolutely not going to know anything. And today what we do is what Gajini did. We write it. We write it and then store it somewhere and call it as memory and say that next time when you're seeing, check whether that memory has this or not and then proceed. But the model does not learn anything. It doesn't change its probability distribution at all. But what needs to change is learn from usage. How do we do it? Unsolve the problem. So let's talk about tool calling. Tool calling is interface to the world. So again, as I said earlier, if you look at all AI systems, 2 parts. The bottom part is your API calls that you're making to traditional software system. Understand this. This system will continue to be there. And the top system is your AI models. So the interface between the two is your tool calling interface, right? So what does that need? Structured output. And as we discussed earlier, the tool calling using the constraint decoding that solved that problem in a pretty acceptable way. It's really a good breakthrough. And how many of you know about MCP, Model Context Protocol? Right? So yeah. So if you look at Model Context Protocol, all it did essentially is to standardize the format to say the author of the tool can specify it in a certain way. Now you can change any model that you want. You can use it with OpenAI model. You can use it with any other orchestrator. You can bring your own model. There are enough middle tier code that can take care of how to go map all these things to the corresponding tool calling semantics of each of those models. So that's one thing. But again, where does it fail? There are places where the model reasons that, oh, in this case, I need a tool like this. So that the model can say that this is the intent I want to solve. But there's no tool description, or the closest to tool description is something. So it will try to go call that. It won't match at all. So that is a problem. Sometimes what happens is the parameter that you get for those things are incorrect. So the first thing is which tool you should be calling, and second is what's the parameter you should be passing for the tool. Both fails. So that leads to this question of A, how do we standardize the semantics? Number one. Number two, can we simply go and tell that we specify the system and say that these are all the functions that the system provides, and we basically ask the model to say generate the code on the fly and execute. Good idea, but also a risky idea. The reason is that if you let the model go and generate some code on the fly, who is going to verify that that code is correct? So what it is allowed to do need to be restricted. But these are all again unsolved problem, as in everybody is aware of it. We need to go spend the time, put the energy to go and make that progress. But that's a very, very important thing. Why is this important? Again, if you're able to go control this interface layer correctly, you can drive better reliability. So let's double click into breaking the system into different layers. So at a very, very high level, this is like simplified significantly. If you take a model, this is essentially what's happening. This model, you can put any model you want. You can take a small language model like a 5.4, or you can pick your super large model. Your input is a series of tokens. Your output from the model is not tokens. From the model is just logits. It's basically the distribution of probability across all the tokens that can come next, which is the complete vocabulary. If you say that your vocabulary is 200,000 tokens, it's going to give you a 200,000 vector saying something like, hey, this is a distribution of it. That's what you get per token output. There what you have is this sampler. The responsibility of the sampler is to say that out of the 200,000, I'll pick one. And that one can be based on max probability. It can be somewhere in the top K, any of those things. Or you can say, I will pick the one which is in the top K and also follows this constraint, this condition check. So that's exactly how you implement your sampler. So the sampler's responsibility is two. So at the end, you go and take that output, take the sample to token, and then you say, okay, generate that as output. Or you simply take that and then push it into the input to say that this is the next token and keep continuing the same loop till you generate the whole output. So this is at the core what we have. Now within the model, you can now go and tell that, hey, the model can be trained in all those three ways, right? You can use pre-training, which is practically self-supervised learning, or you can say you're going to do supervised fine-tuning, and you're going to say that I'm going to do reinforcement learning loops. The latest one that we have right now is RLVR, reinforcement learning with verifiable rewards. Now all that can happen in model, but irrespective of how the model is constructed, you can kind of wrap all these things and then say that the contract is very simply, you give me some input, I'll give you some output, and that becomes your API layer. And if you go one step further, where we go and tell, like what we discussed a while ago, you can tell, like if you have to go create memory, where are you going to create the memory? Because the system doesn't remember anything. You're going to keep it outside. So that memory, all the tools that the model can invoke, any optimization indexes that you are having for looking up information or procedures, all that is outside of the system, and that's what's typically called as your orchestrator layer. So if you take, how many of you use GitHub Copilot or Cursor or any of these things? So all those things are orchestrators. So what they do is they manage the tools. What does a GitHub Copilot do? Or any of the coding tool? They basically tell that I have this code base and I'll give you tools to kind of manipulate the individual code files and stuff like that. That's what you get. right? In addition to that, if it has to have memory, all that the GitHub Copilot can manage. So with this, let's kind of look at, if we talk about reliability, where all can we control? Obviously, model. The first and most important system here is the model. Because model offers the most leverage in driving reliability. Today we have next token prediction. Should it be something else? Yeah, that's a possibility to go and explore. Second, we have already seen success with samplers. How? Constraint decoding. What other constraints can we go and add? That's a possibility to go and explore. How can we generalize this further? And third, like this is by far the easiest thing to scale, is you go put all those interventions in the orchestrator layer. The orchestrator can decide which model to invoke. Orchestrator can decide how many models to go and invoke, whether to use one model to evaluate the output of the other model. All these type of things that you can do in orchestrator layer. So if you think about it, orchestrator layer gives you the flexibility to experiment anything that you want. And then you can tell that whichever is successful, you can go drive that into the model, right? So with that, let's kind of look at where we can put all these things together. The goal here is not about me offering a solution. This is to go and say what are the problems that we have, and then we end it with an inquiry, right? 4 points. Today, I would call the current large models as mainframe models, because one of the analogy that I keep talking about is, so if you think about the current generation of AI models, this is practically like mainframe systems and mini computers. At max, with the small language models and all, we have come to Altair type of computers. They are still kit computers. They are still not a PC. What differentiates a PC? PC has standardization. The instruction set is standardized. The architecture, the communication between peripherals and the system is standardized. That allowed for the industry to participate more effectively. So the question is, we don't have the so-called modular models yet. Should we pursue that? It's a question to go explore. So the question is, would modularity enable deeper failure modeling? Important question to go explore. Second is semantic interfaces versus declarative specification, which is if you take MCP, Model Context Protocol, you can declaratively specify, hey, I have a module, all these functions are there. So should we go and tell there is a definition of a semantic interface? Again, TBD. Third is model as a storage versus AI native memory. So what is model as a storage? Today, if you say that the model knows something, what is happening is all the knowledge of whatever you are training is in the model weights only. Now the question is, this doesn't help you to go and tell something like, I want the system to forget this knowledge. I want the system to forget this knowledge or add this knowledge. You can't do all those things. You can't control. So the one orchestrator level solution that we have is through RAG index, but RAG index doesn't always work. You'll see a big difference between when you're using a RAG index to generate the output versus model is providing AI native, like it is a model native responses. You'll see a big difference. Why? Because how it is retrieving that information needs a better solution. And this way, and RAG is like it's like a cheap substitute. It's not a real substitute. So we need to think about what does AI native memory looks like. And lastly, evals. You would have seen GDP val, this val, that val, like, humanities last exam. All these evals are great, but they are all talking about one thing. They are measuring capability. We have very, very few for reliability. So one of the questions to go and answer is, should we invest in reliability evals? So with that, I want to just end with these two callouts. One is, reliability is going to practically make a huge difference with respect to adoption. If you want this to go beyond being a toy, beyond being consumer experience only, reliability matters. And that requires more exploration. Thank you.